Start. So it's my pleasure to introduce the second mini course of the school, which is Wahl, the Generations of Surfaces by Giancarlo Urzu. Please, Giancarlo.
Thank you very much. So you can hear me, right? Yes. So I will be, thank you very much for the invitation to give this mini course. I was here 9 years ago, giving a lecture. I recognize several people that was there. I remember Genia and other guys. Antonio, I think. Right? Yeah. You were here 9 years ago. Yes. Michael, I guess. And so it's a pleasure to be here. So I will be talking about these degenerations of complex surfaces and applications. So my goal is to give an application or maybe a connection, an open problem, at the end of every single lecture. At the beginning, I will be talking about, so that is the plan. At the beginning, I will be talking about continuous fractions. So you will see almost no algebraic geometry in this lecture, only addition and subtraction of numbers. And by the end, I will apply that to Markov numbers and this Markov conjecture. In the second lecture, I will be talking about what you see there, singularities, very particular ones, the ones that are related to these continuous fractions and deformations. And after that, in the third lecture, I will be talking about the rational geometry of these degenerations. So I will be very, very explicit, I hope, very concrete examples, and then I will run MMP. And my plan is to come back to Markov numbers, so by rational geometry of Markov numbers. So by the way, I forgot to say that I have lecture notes that are in the web page with exercises, and my TAs will be doing some of them for you today. So I have two students, PhD students of mine, Marcos Canedo and Juan Pablo Zúñiga. You can see them there. Okay, so now let me start. And also everything that I'm going to write is also there, so I will be changing and you will see at the same time both. And okay, so definition. So if you have a collection of numbers, so say that E1 up to ER is a collection of positive integers. We say that it admits a Hirschenbrock-Young continuous fraction. And this is the notation. So this square bracket, E1 up to ER. And this is going to be the fraction and also the value of the continuous fraction, which is E1 minus 1 over ER, E2, and so on. ER. If the continuous fractions from I to R are positive for every I bigger or equal than 2, and when you have the whole thing, maybe it could be 0. So bigger or equal than 0. So that is the definition. So for example, if you have 2, 1, 3, 2, by the way, this is going to be the length and this is the value of the continuous fraction. So if you have that collection of numbers, you can check that this admits. So this is okay, it admits. Maybe you are wondering, well, I have to check this every time, which is going to be like difficult. But no, we will see soon that there is a birational geometry on these continuous fractions. And there is a blow up, blow down that allows you to work with this easily. You don't need to really check this condition all the time. So this is okay. This is not okay. And why it's not okay? Because you compute and you don't satisfy this requirement. If EI, this is not okay. If EI are all bigger or equal than 2, then this is always okay. Those are kind of homework. So always when you have a sequence of positive integers where there is no 1, it's okay. It's going to be a Hirschenberg-Jung continuous fraction. Now, the way we think about these fractions is not really like that, but as a chain of spheres. So think this way. We have a smooth surface, and we have spheres in a chain. This is what I mean by a chain. It's a chain of P1s, C in a smooth surface. And then think about these numbers as self-intersections, but negative. So minus ER minus 1 minus ER. So in that way, and so we will have a birational geometry, and by that I mean if you have a minus 1 curve, that means that this number is 1, so you have minus 1 for the self-intersection, then you can contract. Or if you consider a node here, you can blow up. So you can introduce a 1, but then you have to increase E1 by 1 and E2 by 1. So we have blow up and down. And by this, I mean the following. So you have a situation like this, U1B, and so on. So this is your continuous fraction, and then you can blow down this direction. So it would be U minus 1, B minus 1. And this is going to be okay. So if this is okay, then this is going to be okay, part of the homework. And also you can do the inverse. So this is down, and this is, well, it doesn't matter. Right? Well, down in that direction, and up. Okay, and so if you try to eliminate all the ones that you have in this sequence of numbers, then you have minimal models of these fractions. Maybe let me give you some more examples going to minimal models. So let me give you some examples. Say, so you have only 2s and minus 1 of them. Then the value of this continuous fraction is m over m minus 1. You can blow up. So this is like a chain of minus 2 curves. You can blow up between in a node of that chain, and then you get 3, 1, 3, and only 2s. See, and this is okay. This is the blow up of that. And actually, you can prove also that the value is the same. So if you do blow ups on nodes of this chain, then the value is going to be exactly the same. It's going to be minus 1. And so on. If you have these, then you can contract That is what I meant. And this is like, and here you cannot keep contracting, so this is a minimal model of the fraction. And then you can prove, theorem, that Hj, continuous fraction, have unique minimal models and what are the minimal models? You have one. This represents a smooth point. I would like to say that you have 0, but instead of zeros, and I didn't allow to have zeros on the sequence of numbers, you have 1, 1. And this is going to represent a P1 with self-intersection 0. Or you can have any rational number bigger than 1. And what I mean by that, so you have 0, Q, M prime, and you compute M over Q. So you have two coprime integers. You compute this M over Q, E1 and it's ER, but you do it in a minimal way with the EIs bigger or equal than 2. And there is a bijection between this kind of sequences and the rational numbers that are bigger than 1. And that's it. These are the minimal ones. So the way we think about these fractions is by blowing up these sequences, these minimal models. These are going to be very important for us. These are called the continuous fractions of 0. And these are going to be the one related to the singularities. So here you have singularities. Here you have 1p1, and this is a smooth point. Okay? Let me see if I can show you a bit of this. Okay. This was definition. Any questions? You see, very simple, plus and minus. Oh, and this is the key to blow up. U minus 1 over V is equal to that, arithmetic. Sorry? What is the meaning of? That if you contract, if you have one that is on, and you keep contracting, you will reach only one, either that, this, or just one rational number here. Yeah, there is no, yeah, like Hirschenbruch surface, you have to choose, no, you go directly to one. Another question? No. I cannot hear, can you say? When you say that minimal is thing, you mean that there is no one in the yeah, in here, yeah, that is unique, that you have anything that admits a continuous fraction, then you can blow down and blow down, keep blowing down, and you reach one of these options. That is what I mean. It's a very simple exercise. But then unicity means that any rational number admits a unique. Yes, exactly. Yeah. Okay. So now some tools to work with these continuous fractions. I wanted to do an entire lecture on these continuous fractions because this is the arithmetic behind the birational geometry or anything that you do with these degenerations. So I want you to be familiar with this. So this proposition is key to prove many properties. If you have coprime integers, and so I'm thinking about this minimal continuous fraction, then you can express everything in terms of matrices. So you can prove this equality. So this is a 2 times 2 matrix with these numbers. This Q inverse is the inverse of Q between 0 and M mod M. So Q inverse is congruent to 1 mod M. Q inverse between M and 0. And this is equal. And now you put the numbers in the continuous fraction. E1 minus 1, 1, 0. And so on until ER minus 1, 1, 0. That is also in the homework. Not difficult. So you understand, you codify the M and the Q doing this multiplication. Corollary, you know, if I give you M over Q minimal, E1 up to ER, then if you flip the numbers, so you go from ER to E1, then you have as numerator the same M, and denominator the inverse of Q mod M. And you can prove it with this exercise. Homework. Okay. Also, I wanted to mention maybe that is something that I will show, that there is a connection between these continuous fractions, negative continuous fraction. I realized last week I was giving a talk and somebody in dynamics told me that these are called backwards continuous fractions, and they are used in dynamics now. In talks in dynamics, I always see continuous fraction with plus, which is the Euclidean algorithm, but now it seems like they are using the negative ones, and they call it backward continuous fractions. I didn't know. Okay, you have this. Yeah, this is the thing that I wanted to mention. Oh, let me see what happens. Wait. That they are directly related with classical Dedekind sums, in case that you know about that. But there you have the definition, these kind of sums, where that symbol is defined here. So you take the number, subtract the integer part, and then minus 1 over 2. They appear in the Dedekind eta function, in the functional equation. You have an error, and the Dedekind sum appear there. These Dedekind sums appear in geometry. There is actually a book by Hirschenbruch and Sagier on these Dedekind sums. And, you know, it's hard to give a formula, a closed formula for that sum, but you can do it using this continuous fraction. You see, here you have the sum, and there you have the EIs of the continuous fraction, the inverse of Q and Q over M. And actually, that equality is another formula in algebraic surfaces. That is also an exercise in the notes. Just computing a covering, you can recover. More or less, this has to do with the holomorphic Euler characteristic. The length has to do with the topological Euler characteristic, and the rest is the square of the canonical class. Okay, so now I move. So among these minimal continuous fractions, the most important ones are the Wahl chains. So now I want to define them. So it's very strange, maybe, very particular fractions, very particular rational numbers. So you take, so this is definition 2. You take now coprime numbers, A and N, coprime, and then consider this rational number, n squared over na minus 1. And you know there is a chain, a minimal chain, corresponding to that. Those are wall chains. Now, these are important because when you want to understand the formations of these singularities, the cyclic quotient singularities behind this, then all you need is to know about a certain relation between these singularities and that particular one. We will see that in the next lectures. But how to work with this, right? N squared over Na minus 1, what is the fraction? Well, you can check. So this is not part of the definition. You can check that there is a symmetry. So, fact, there is a symmetry. So if you consider a wall chain, that means a sequence of numbers so that this is the rational, that the value is this rational number, wall. Then, if you go backwards, if you flip the fraction, then this is also wall. And the reason is the corollary that I just wrote, because this is n squared over Na minus 1. And for the other, you need the inverse of this q, which is easy. Instead of a, you use n minus a minus 1. That is the proof. And then you have something that I just call mutation. So you start with a wall chain, and then this is wall. And then you apply this. You add 1 on the first one. Keep going, E2 up to ER minus R. You don't do anything with them. And then you put a 2 at the end. And this is wall. This is also something that you can check. If they, so, well, it turns out, for example, if A is 1, then, no, that could be 1. Yeah, this is used. So, for example, when you put, sometimes if you don't say coprime, then maybe we're talking about these A-type singularities, and I want to divide them. Like, I really want to, so wall chains are very different to these A singularities, but I don't remember what number I have to put there. It's n, exactly n, right? N squared minus 1. For example, something like A equals to n, and so A and n equal, say, then this would be an A singularity, and I want to eliminate that case. So maybe this coprime thing also appears when you compute, because there is another definition of these wall singularities. These are the ones that admit these Q-Orenstein smoothings that I will talk about. And when you put that definition, then you prove that it has to be like that with N and A coprime. There is also something about K squared. K squared for these singularities has to be an integer. Typically, with any fraction, with any cyclic quotient singularity, this is not an integer. But if you say, I want that to be an integer, this is equivalent to be a T-chain, which is a bit more general. But then you have this, you see in the proof that you need N and A coprime. So from here, no. From here would be like a capriccio. Yes. I didn't get it, but okay. Yeah. So then the theorem is that you can create all of these wall chains using this symmetry and mutation, starting with 4. So 4, maybe I will write that example. So example, what is 4, right? 4 is 4 over 1, which is 2 squared, 2 times 1 minus 1. So this is Wahl. This is the smallest. You have 0, a equals to 1, n equals to 2. So, and then this is the smallest, and from this one, using those operations, you can prove that you can obtain all Wahl chains. And I think that, and then you will see a tree, and I will show you that now. So there you have 4. You know, by adding 1 to 4 and then adding an extra 2, you have phi 2. But, and also you can have 2 phi, but 2 phi and phi 2 for us is going to be the same. So you just go from 4 to phi 2, but on phi 2 you have 2 options. You might add 1 on the left or 1 on the right. And then you have, if you add 1 on the left, you have 6 to 2, and on the right you have 2 phi 3. And then you keep going, and you have this tree. Theorem, whenever you have something like this, then it belongs to that tree. Yes? Geometrically, what this means for the surface? Yeah. Why take only one direction and not the other?
Why does it matter that you can go from just one number by those two different operations?
So I don't understand why you choose that order and not the opposite? Or?
Maybe on the previous slide.
Yes.
So this term, like, I guess, why is this useful?
Why is useful this? It's because this is kind of classification of all Wahl chains. So after this, I can think about Wahl chains, looking at these.
Actually, so with this theorem, I mean, if I looked at these papers, would I find a theorem about continued fractions, or would I find a theorem about, do they prove it using?
No, this is continued fractions. You use nothing.
And they don't prove it geometrically, they prove it.
No, yeah, with continued fractions. So maybe that is the question. I don't use anything from algebraic surfaces to prove this kind of thing. This is completely combinatorial.
I guess the question, or my question is, like, if you do mutation into the set of numbers like that, are you doing something geometrically? Like, does it correspond to something?
Yeah. So maybe I will wait for that to show you. Yeah. Okay. You want to see how these continued fractions appear geometrically. Yeah, you will see that next lecture, I think. It has to do with elliptic vibrations. But I want to wait until then. So right now, it's only combinatorics, adding and subtracting. Yes?
Are there cases where you can't permutate any of the values and you keep going with Wahl?
Permitting.
The symmetry is just going from...
It's when you flip it. Yeah, symmetry is flipping.
Yeah,
and the other one is very particular. You add 1 and then add a 2 at the end.
Yeah, the values from
How the values change, we will see that.
Okay.
Yeah, we will see that. There is actually a Fibonacci thing happening. We will see that in a moment.
More elementary question maybe. How is 253 obtained? Is it notation?
What?
How is 253 obtained? From 52, right? You have 253 there.
253, yeah. You go from phi 2, you add 1 on the right, so 3, and you add a 2 on the left.
But
Because,
isn't 253 is obtained by notation? No.
yeah,
Is symmetry?
yeah, symmetry and mutation. Yeah, we are mixing that.
So it is 352.
Symmetry again.
Yeah.
Symmetry again.
Yeah. Okay, that is very good. And then corollary, you can compute things like this that are going to be useful when we compute, for example, self-intersection of canonical class. You know, I show you this Dedekind sum formula, and I told you that there is some self-intersection of canonical class that involves this sum. So for Wahl chains, you have that sum is exactly the length plus 1. easy exercise from the algorithm. And then you have this formula for detecting sums. Okay. Hmm? Yeah, we will see in a moment. It's coming. Well, maybe I can tell you now. So, example. Because this is going to appear when we compute discrepancies of these singularities, yes? Yeah, we will have something else, but the ones that interest us, and so related to these Wahl singularities, they start with 4. 4 is important. I think so, yeah, maybe, yeah. Actually, if we start with, you remember the 2 Wahl singularities? Yeah, with 2, it's kind of important for Markov numbers, if you start with 2. But that is the only one that I know, 2 or 4. But 4 is Wahl singularities. I don't know what the application is for 3. 3 singularities, yeah, could be. Yeah. Okay, the example. So say I take this 2, 6, 2, 3. And you don't want to compute the continuous fraction. You want to compute n and a without computing the continuous fraction. So this is the algorithm. You know, you obtain this chain by adding 2's to the right, like jumping like this. So you start with 4, you go to 5, 2, then you go to 6, 2, 2, so you jump again. And now you go like this, from this 2 to this other 2, so this becomes 3, and this is the process, this is the algorithm. This is what we do. So now you started here, this is the center of the chain, and you put a 1. And now only at the beginning, you will add this 1 to itself. So 1 plus 1, and you say that the next is going to be 2. And now, for the next, you add the ones that you have on the extremes. So 1 plus 2 is going to be 3. Then 1 plus 3 is going to be 4. And then 4 plus 3 is the n, which is 7. And if you look at this continuous fraction this way, so this is equal to n squared over na minus 1, then a is 4. If you do it that way, is n minus 4, 7 minus 4, which is 3. So that is the way you compute, using an example. So later, maybe tomorrow, I will give the formulas. And it's Fibonacci because more or less you are adding the 2 numbers that you had before. For example, to have exactly Fibonacci, you have a situation like this. You put only 3's and say a 2 at the end. You know, you keep jumping in both directions. You see 5, 2, 2, 2, like this. So always you are adding like 1, 2, 3, 5, 8, and so on. And then you get Fibonacci numbers. If and only if. Well, whatever. Okay. Now I want to talk about a little bit about the dual fraction and the zero fractions, which are going to be important. Yeah, you can also, yes. Yeah, there is, exactly, yeah. So, yeah, I will show that later, yes. Okay. So, well, there you have the definition of the dual fraction. So dual fractions, so given a fraction, we will soon, tomorrow, we will have a cyclic quotient singularity associated. But then to study the formations, we need the dual of that fraction. So the dual means you change Q by M minus Q. This is going to be V1 to Vs. And that is definition. So for example, 4, which is just 4, then 4 over 3 is 2, 2, 2. Compute. Theorem, where you can see it there. If you consider Hirschenbruch-Young continuous fraction and the dual, then you can glue them together to get a continuous fraction of 0 in that way. So the theorem is E1, ER, and now you put a 1, and the other one, you flip it. So it's like Bs have to be 1, and you can check that this is always 0. And this is if and only if. So if you have two continuous fractions where all the numbers are bigger or equal than 2, so that you put that here a 1, then these two are duals. And this is geometrically saying that if you start with P1 self-intersection 0, like a fiber of a P1 fibration, then by means of blow-ups, you can achieve this situation, any situation like this. So the continuous fraction of anything and the dual blowing up. Okay, so from that theorem, you have this diagram way to compute the dual. So let me show you, for example, this 11 over 2. You compute, you have 6, 2 as continuous fraction. And then from that 6, you subtract 1 and put 5 dots, like I did. So 1, 2, 3, 4, 5. And then for the next number, again, subtract 1, and you put that number of dots, but in this case, it's just 1. So to recover the fraction, of course, you add 1 and 1, and you get 6, 2. But the cool thing is that if you do it down, like it right there, then you add 1. You have 2, 2, 2, 2, 3. And this is exactly the dual of 11 over 2. That thing is exactly the same as this theorem, a geometric way to see it. Here you have another example, 2, 3, 2, 2. And you see 2, 3, 2, 2, like that. And now you add this way. So you get 3, 4, and so 11 over 4. Okay.
This is Riemann-Schneider.
Yeah, Riemann-Schneider. Dot diagram, exactly. Yeah, I'm not citing anyone in this, but okay, in the notes, you have the paper citations of everything, all names, everything. Okay. Okay, so these continuous fractions of 0, that's it, the whole MMP on 1, 1. That is the continuous fraction of 0. Have to do with the formations of the minimal Hirschenbruch-Young continuous fractions, which are going to be the cyclic quotient, two-dimensional singularities, which are governed by these Wahl singularities. So this is a summary of what is going on. We will see this in the next lecture. And so it's important for us to look a bit more on these zero continuous fractions. So here you have the list. So here I go step by step, doing all possible blow-ups, increasing the length. So for example, you start with 1, 1, which is the minimal one. Then you can blow up in the middle or on one of the extremes. And so you get 2, 1, 2. You all see that, right? And then 1, 2, 1. So those are the zero continuous fractions of length 3. If you go to the next level, so length 4, then there are more options. There you have all the options. And these options increase a lot as you increase the length, because actually you can prove that you have this many options when the length is S. So this is the Catalan number. And why is that? Because this is related to triangulations of these convex polygons. So how? You have, maybe I will write that down. So I don't remember the time. When did I start? So it's until 12. 40? Great. Okay, so these zero continuous fractions are related are in a one-to-one correspondence with these triangulations of convex polygons. So let me explain that with an example again. For example, you have these pentagons, like I wrote there. So maybe you're wondering, or maybe you already decided what these numbers are. You see, this is a triangulation. You draw diagonals that do not cross so that you form only triangles. And then these numbers is the number of triangles that has this vertex, this point as a vertex. So here I have 2, so you put 2. Here I have 2, 2, this is 1, this is 3, and this is 1. And then those are all the options, how you recover zero continuous fractions from these numbers. So you forget about 1 point, or you fix, if you want to have the list, you fix 1 point, like the vertex on the top, and then you read this way, zero continuous fraction. And why is that? Because if you erase a triangle, for example, so how we create these continuous fractions? We start with this 1, 1, and then you blow up, right? You get 2, 1, 1, 1, 2, and so on, until you get this. But what is the creation? When you add a 1, it's like inserting a triangle. And so you have a polygon with one more edge. And also you have the blow down. You erase the triangle, and now you decrease this by 1 and this by 1 until you get, so down, you will go directly to the triangle. So 1, 1, 1. Right? So that is the connection, and then you can prove that the zero continuous fractions are in bijection with these triangulations of convex polygons. And so people counted them, and those are the Catalan numbers. And so you have the relation. Each of these, well, we will see how these connect with the formations of cyclic quotient singularities. But it turns out that cyclic quotient singularities related to these fractions. It turns out that if the EIs are big enough in relation with the length, then you have as many as triangulations of the corresponding polygon. So the number of components of this deformation space is huge. And each of them has to do with a triangulation of this polygon. We will see how. But the how is connected with this, and this is the last definition, I believe. So now take a minimal fraction again. So think about a cyclic quotient singularity if you want. This is 4, take that. And then we say that this admits a E0 continuous fraction. I created that for these lectures. This is nowhere. I mean, we have this thing in the papers, but we don't have a name. So E0 continuous fraction means that you have E positions in here, in these numbers, so that you subtract a certain amount, Dij, on each position, and then you get a zero continuous fraction. So that is going to be the game. And we call it small if the subtraction is by just 1 everywhere. So admits E0 continuous fraction if there are positions, E1, different positions until IE, and integers Dij bigger or equal than 1, so that you go and subtract on those positions. So EI1 minus DI1, and the rest stays the same.
You subtract from E's or from B's?
Yeah, I went to the dual. Thank you. Yes, because we will work with these E0 continuous fractions on the dual. This is the cyclic quotient. We need to go to the dual, and there we work with this. Yeah, that is why we have B's. Okay, M. Thank you. Yeah, this is B1 up to Bs. And so this is B, this is B, E minus E, E, and this is 0. So this is going to be the connection. For the cyclic quotient singularity, you have this dual, and you wonder if there are positions where I can subtract a number, an integer bigger or equal than 1, so that I get 0. If you have that, then you have a component of the deformation space of the cyclic quotient singularity. We will see that. And then small, if the di's, j's are all equal to 1. So here you will see now another characterization. This is going to be small. Another characterization of Wahl singularities. I think that is the next one. So are there any questions with respect to this definition? E0? Yes?
What is the word after E goes count?
After here? Such that dik bigger or equal than 1, above that? Continuous fraction, E0 continuous fraction? Okay. I cannot hear.
If this admits an E0
Yes?
fraction, if the dual also, does the dual also admit
No, maybe not. I don't think so. But I don't know. Yeah. Okay, so I have the continuous fraction. I look at the dual, and then I wonder if it admits E0 continuous fractions. Okay? Then you can prove, this is also, well, there are two, well, you will see. Well, there you have an example. 19/7 is 3, 4, 2. You can compute that. Then 19/12, which is the dual, you have 2, 3, 2, 3. And now you try to subtract in all places and try to get a 0 continuous fraction. And it turns out that you have 3 options, exactly 3. So you subtract in the first 2 positions and in the last, like I showed you. And this is going to give you 1, 2, 2, 1. And you see, you can contract that to 0. You know, you contract 1, you get 1, 1, 2, 1. And then again, and you get 1, 1. And so this is 0. And actually, you see that the first line always happens. If you have a continuous fraction and you look at the dual, you have these numbers that are all bigger or equal than 2. You can always subtract on these numbers to get only 2's in the middle, 1 and 1 on the extremes. And that continuous fraction, so it would be, well, that E continuous fraction has to do with the arcing component of the deformation space of the cyclic quotient singularity. And then you have these other 2 options, and no more. Then you have, for example, this other characterization of Wahl chains. Hirschenberg-Young continuous fraction at small 1, 0 continuous fraction. So you have the dual. There is one position where you subtract 1 and you get 0. So that position has to be a 2. Otherwise, impossible to get 0. If and only if it's a Wahl chain. That more or less is that is a nice exercise because you can see how these Wahl chains are created from the dual of them. I think that I will come back to that, but this is an easy exercise. This is not. This is a challenge, which is a theorem that appears in a paper with Genia. Because it has to do with the particular extremal P resolutions that we will see maybe on Wednesday when we see birational geometry. If you have a fixed continuous fraction, and now you wonder, are there two positions where I subtract 1 in each so that I get 0? Well, sometimes you can. Many times you cannot. But what if you have one? Is it possible to have another one, another pair of positions? Yes, that is even more difficult to find, but it happens. Can we find another pair, like 3 pairs? No. So at most 2. So if you have a simple proof of that, maybe let me know. This is a bit difficult to prove. I think that I have examples of that now. Yes. So for example, 15 over 4 is 4, 4. The dual is 2, 2, 3, 2, 2. But now you see that there are 2 pairs where you can subtract 1. So they are marked with red bars. You have 2, 1, 3, 2, 1. That is 0. You can contract to 0. And the other one is the symmetric, because this is symmetric. And so you have 2. In the next one, something similar happens. It's also symmetric. So if you have one, you have the other one. But it's not always like that. In the third example, you have this situation. So it's not because of symmetry that you have 2 and at most 2. There is something else going on. And here you have another situation, but this is also symmetric, but it's bigger. Hmm? If I take like other, no, I don't know when you go beyond, I don't know. With 3, for example, I don't know. Yeah. Because I haven't had motivation to look at that, but there are a lot of combinatorial things that we can think, but I need motivation to go for it. Yes? This one? Yeah, at most 2. That theorem has to do with the following. When we perform a flip, we will see flips soon. So you have the negative curve. There is a contraction to a cyclic quotient singularity, and you are looking for a extremal P resolution. This theorem says that if you find it, be careful, because maybe there is another one, but at most there are 2. It would be very nice that only one, and then you have the flip like immediately, but it's not the case. So you need to check something. But also it has to do with something else that we call wormholes, but maybe I will not mention that. Okay. Continue, and now I will go to the big challenge. Okay. So now maybe 30 minutes for Markov numbers. So this was the introduction to Hirschenbruch-Jung continuous fractions. We saw the general picture, the minimal models, wall chains, and 0 continuous fractions. And this thing about admitting a 0 continuous fraction. Everything has to do with geometry, but that is coming from tomorrow. Coming up. And now I will talk about an application. So I have a preprint with my student, Juan Pablo Zúñiga, about the birational geometry of these Markov numbers. So, and now we start with that. It's like a mini talk about that. Okay, so this is Markov. So this is the big challenge. Related to these fractions is this Markov conjecture. So you have this equation, x squared plus y squared plus z squared equals 3xyz. It appears more than 100 years ago in the work of Markov on these binary quadratic forms. He was looking at the minimum values of these real binary quadratic forms. And when you look at that, he realized that naturally this equation show up. And he defined the Markov forms and so on. I don't know, maybe you have heard about this Lagrange spectrum and Markov spectrum for real numbers. So it has to do with that. And then a Markov triple is just an integer solution of this Markov equation. So on the positive numbers, that is a Markov triple. And then we have, again, symmetry and mutation. And actually, there is a relation with Wahl. Well, this is symmetric, so all permutations of the Markov triple is a Markov triple because it's just symmetric. And then you have this mutation. If ABC is a Markov triple, then AB, and then this formula, 3AB minus C, is also a Markov triple. Okay. Okay. It turns out that with those operations, you have a tree similar to the Wahl tree, but now we have the Markov tree. So you start with 1, 1, 1, which is a solution. 1 plus 1 plus 1 equals 3. And 1, 1, 2 is also a solution. And then you continue mutating and doing this operation, the permutations. And you obtain this tree. Now in this tree, I put the Markov numbers are the coordinates of the Markov triples. Okay? And this is 2 point. Yeah. So in this tree, the biggest coordinate is going to be the last. So they are organized from smallest to biggest. And then, for example, here on this line, which is in blue, you have only Fibonacci numbers, but in odd positions. If you do the Fibonacci sequence and look at the odd positions, that is what shows up. And this is just because of the mutation. And if you change to this, so this is governed, if you want, by 1. When you want to keep 1 and mutate the others, then you get Fibonacci numbers. If you stop here and you want to keep 2, so you move it to be the smallest, and then you keep it forever and mutate the others, you get the Pearl numbers, which is more or less the same formula as Fibonacci's, but with a 2. But then those are the only cases where you have only one branch. For the rest, you have 2 options for the smallest Markov number. So for example, here you have 5, which is the biggest, and now I want to move it to be the smallest, but there are 2 ways. One way is this, and the other way is that. And then you keep the 5 as the smallest and mutate the others, and you get these 2 branches. And so on. And you can prove, it's not obvious maybe that you can prove that this is a tree. It's not super hard, but. So here you have all the solutions. Okay? So now I will talk about the Markov conjecture, which is not due to Markov, but to Frobenius. And actually it's called Frobenius uniqueness conjecture. And this is Frobenius. So on 1913, he proposed the following conjecture. If you have a Markov triple, 2 Markov triples, where the biggest is the same, then the other has to be the same too. So the highest, the biggest Markov number determines the other 2. That's simple. And it has been like 111 maybe years, a challenge for many people. And there is actually, this is a well-known conjecture, but actually when I talk to mathematicians, nobody knows about it. But there is this book. So there is officially a famous one. There is this book by Martin Eichner, which is one of the authors of the proofs from the book, together with what is the name of the, Ziegler Eichner. He passed away last year, Eichner, on October. And there is this book where this Markov conjecture looks something very specific, like Fermat last theorem or something like that, very particular. But it turns out that appears in many branches of mathematics, and he realized that people maybe were not aware of that, and then he collected all the connections, many connections, in that book, with an emphasis on this conjecture. And also explains the Markov theorem on quadratic forms, approximation of real numbers. There are connections with hyperbolic geometry, combinatorics, groups, etc. But he didn't write about connections with algebraic geometry, and there are some that we point out in the briefing with that some of them were well known. There are new ones we think related to these Wahl chains. Okay, so via this birational geometry of degenerations. Okay, so this is going to be in the last lecture. I will explain how this Markov equation appears on degenerations of, actually in the previous to the last, on degenerations of P2. It's like a replacement of P2. You know, when you run birational geometry on a smooth projected surface, you keep contracting these -1 curves, and then you have either this model with canonical class Neff, or you have these ruled surfaces, or you have P2. On degenerations, you have something similar. We will look at that soon. And the replacement of P2 is essentially the Markov picture. So I will tell you about that soon. And you know, this is like the end of MMP, but it turns out you can run anyway MMP on these degenerations. And when you do it, you get these combinatorial pictures and equivalences with Markov conjecture. Okay, so what is the equivalent conjecture to the Markov conjecture? Is this one. So given any integer m, there are at most 2 coprime integers q, so that if you write down this Hirschenbruch-Jung continuous fraction, which is 5, and then the continuous fraction of m over q, then 2, then after that, you have the dual of m over q, but flipped. And in a formula, is m over m minus the inverse of q. But it's just the dual flipped. And then 5 again. Then say that you have this chain of numbers, and you see that this chain of numbers is actually a wall chain, a 2, and another wall chain. Anything. Wall, 2, wall. Then there are at most 2 q's where that happens. Or if you want, if there are 2, then the sum of them, if there are 2 q's, then the sum of them has to be n. So if you have 2, it's just, it is this or the flip of that, and no other. One can prove that actually if that happens, then m has to be a Markov number. But the problem is, are there any other way to have wall, 2 wall? Let me show you an example so that you can see what is going on with the Markov number 29. Yeah?
So the 2 in the right-hand side has to be this.
No, it's another 2. No, it's not that simple. No. It's another 2 that you need to find. And there are certain things that have to happen, but we don't have enough information yet to say, to verify the conjecture. Well, we can talk about that later. Oh, yes?
What is the meaning of m over q? Is that observation?
What is the meaning of m over q here? Yeah. Is the continuous fraction, the minimal one. You write down the chain of numbers. And here you have the dual, but flipped. I think that I will show you. So now we will see many examples. I have some time to. Yes, exactly. If there is one m like that, then m is Markov. Yes, we know that. Okay, here you have a list. You know the problem with Markov numbers is that they increase very quickly. So it's hard to give examples, but this is maybe nice enough. 29. So for 29, I have here this column are the q's, so from 1 to 28. And then I write 5. Then the continuous fraction of 29 over q, then 2, then the dual, but flipped, and then 5. So this is the list. And now in here, you want to find wall, 2, wall. So this is Markov. It has to appear, and you see it. For q equals to 7, you have 5, 5, and then 2's. So you have this, 5, 5, 2, 2, 2, and that is wall, because you reverse the process, you subtract this, you have 3 2's, subtract 2 5, you have 2 5, and then 2 5, well, you go to 4. It's wall. And then the next one is, you see that there will be a 2, so let me write it like this. There is a 2 after that, and then we have 2, 2, 2, 8, 2, 2, 2, 5. And this is also Wahl, because you subtract these 3 2s to 5, you get 2, and then you subtract 4 positions with 2s to 8, and you get 4. So this is Wahl to Wahl. So if you see one of them, then you must see another one, because there is a mirror in the middle. So all these fractions, now you flip them all, and you continue down. You see there is a symmetry. And so you will see the other q here, which is 22. 22 plus 7 is 29. But there is no other q. That is Markov conjecture. Well, for 29, you can check it, but nobody has been able to do it for other m's. I mean, for m, I think smaller than some very, don't remember now, but very huge number, maybe something like that, has been checked. That is okay. And it's not too difficult to check. And also, when m is Markov and has this form, p to some, so a power of a prime number, or 2 times a power of a prime number. This is okay, and this is okay. This is in the book. I don't know, really. I don't remember the names. But the proofs are there. They are not.
Can you prove it using this?
For primes? No, I don't think so. Well, I don't know. I haven't tried. I don't see how. No, I cannot hear anything.
Yeah, so if I have this lock chain, there is a 2 that splits it into
Yeah.
wall. Is this position unique?
Unique, yeah, you can prove that. It's not that easy. You can put it like an exercise also. We call it marquitos, that there is only one way to do this. So if you fix the continuous fraction and it works, there is only one way to work. Yeah, you can use that, for example, to try this conjecture. Okay, this is just to write down, another number, and here nothing happens because 11 is not Markov. You will not see that symmetry. And I am about to finish. I will put some equivalences in algebraic geometry to this Markov conjecture that appear at the end of the introduction. These are the ones that I know. So the first one has to do really with just numbers. It's not really algebraic geometry. But this is let me talk about the second one first. So in the second one, P2, the projective plane over the complex numbers, this is rigid. But it degenerates. So you have P2. So you cannot deform really to something smooth, because it will be P2 again, but you can degenerate, and this will be about degenerations, for example, of this P2. So you will have certain singularities, and actually, when it happens, if you put the restriction that these singularities are quotient singularities, then these singularities have to do with these Wahl chains, always. They are going to be Wahl singularities. But say that we have only one singularity, just to put it easy. So one singularity, this is my picture. Here is a singularity, like a cone. This is a surface with one singularity. And here I have a Wahl chain, so there is an N and an A. So Markov conjecture is this. If you have a degeneration like this, where you fix N, then A is fixed. So if this is fixed, then A depends on this N, is fixed also. That is Markov conjecture at the level of geometry. And then this number A, more or less, is encoded by this number C that appears in the first one. So you have this number C that is a solution to the equation x squared congruent to -1. Sorry, this is No. C is the Markov number. Sorry, here I have a chain of notation. The number, this A, has to do with the RC. So you have a Markov number, and you have this equation, x squared congruent to minus 1 mod C, the Markov number, has only two solutions with weight RC, but the weight, we are talking about this, A, for some Markov triple ABC. And the other has to be C minus RC. So there is this number, which is like the Q, like the A, RC, which has to be unique. Then you have the degeneration. Then there is something about exceptional vector bundles. So, you know, when you have a vector bundle, as you saw today, you have this rank, you have the degree, you create, so say we are on P2, so the degree is going to be the intersection of the first Chern class with a line. This is going to be the degree. And then you have the slope. And you know, by tensoring, you can move this slope to make it so big or very small. But there is at some point, you pass through the interval 0, 1 over 2. And so you have a slope there. That slope is the only slope that you can achieve for a rank that is a Markov number. So there are no, for the same rank, which is going to be a Markov number, you cannot have two slopes in that interval. That is equivalent to Markov conjecture. That was noticed by Turing. And this is mentioned by Rudakov, who made the bridge between Markov numbers and equations and these exceptional vector bundles. Exceptional vector bundles are these ones that do not have any ext. And the ohm is C. And this has to do also with these degenerations. Maybe I will mention something about that. So for example, 2 weeks ago, there was a paper on these vector bundles of a given rank and degree on Del Pezzo surfaces. I think that can be maybe solved also using the theory that I will show in the next lecture. That kind of questions can be maybe attacked with this theory. Not exactly with this, what is coming. And okay, you have that. Yes. And now you have this other three that has to be with the combinatorics that appears when you work with birational geometry of these degenerations. You have these two that I didn't mention in this lecture, and the last one is the one I just mentioned. And so we have these three equivalences also to the Markov conjecture. And that's it. Maybe I can continue tomorrow.